The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the Research Results webinar. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. Questions will be discussed at the end of the presentation. So please note the slide number if possible, if your question refers to a specific slide. With that, we will go ahead and turn things over to Professor Gunnar. Hello.
Hi, good afternoon. So, hi everyone. Thank you very much for joining this presentation. Today, very nice, beautiful weather in Toledo, and this photo also shows that condition. We are talking about a signature bridge located in Toledo crossing Maumee River. I would like to start with my acknowledgements. I would like to acknowledge ODOT Technical Advisory Board, David Geckel, Jared Bax, ODOT Program Administrators, Jill Martindale, Jennifer sorry. All right, I think something happened. All right, Jennifer Springs, University of Toledo faculty, Dr. Douglas Nims, Daniel Georgiev, and my fellow graduate research assistants, Suraj Dungal. Special thanks, we did a lot of site work. You are going to see his photos soon. Yugesh Maharjan, as well as Sandeep Bajagain. So they all contributed tremendously to the success of this project. So the focus is stay cables. They are the most critical component of the cable stayed bridge. The main concern is corrosion of the steel strands. Plus, there could be other deterioration conditions, which could be section loss, pitting, breakage, nicking, compromised grout or grease, voids, water infiltration. So this is a proactive project. Bridge opened to traffic in 2007. It has been quite a number of years since construction. So ODOT wants to have a proactive, non-destructive evaluation strategy in place to monitor the conditions of the stay cables. Are there any corrosion, any deterioration? Is it started, or when it's going to start in the future? So this is looking into that condition. What makes the project unique and as well as interesting to us as a researcher is strands, because this bridge is unique. Strands are epoxy coated. These are the actual photos from samples received from the bridge. But what makes it unique is that there is no grout. These are non-compacted, so each strand continues all the way to the top of pylon. There's a saddle, it goes back, so there is one-to-one positioning, so they never change the positions. They are not grouted, and they are separated by cheese plates. So these cheese plates are put at certain intervals. It's not everywhere, right? So the photo you see from the construction shows the cheese plate at the damper location, right? So they are pretty far away from each other. In between, there is nothing. Strands are non-compacted. This is a traditional condition. These are compacted. You can see all the strands together with the grout filler. So this is the case we have loss of NDE in place. But because of our unique non-compacted situation, which is, by the way, in many cases a good approach for corrosion deterioration, and we can talk about it later on, but non-destructive evaluation methods are really lacking because we don't have this very common. So objective is to determine NDE method for monitoring, but we would like to use existing technologies. This is not about developing a new technology which would take 5, 10, even 20 years. So it's about existing technologies as well as a long-term monitoring and assessment plan. You can see the research stages. This is the research phase, which we love doing it. Outreach is all about seeing what's available, talking with vendors, costing, timeline, do they have it available? Sometimes they come from Europe, the instruments. And finally, application, whatever we selected, we get to use it and show that it works or it doesn't work. So that's what we did. It is a big bridge, right? So you need to categorize it based on priorities, right? So we have two important zones. The first one is anchorage zone. The second one is free lengths of the strands, which I'm going to show it to you in a photo. Anchorage zone is the most critical location because, as you know, you have a mass of steel. It's coated with epoxy. Typically, if you have corrosion, it would start from the ends, which represents the anchorage zones. The other thing is the water runoff and pedaling at the anchorage zones, because typically anchorage zone is at the dead end location, so you might have water at that location available for corrosion. So these are from literature. You can see when they open anchorage zone, they see pretty bad conditions. It's rust corrosion, and you can see they are opening the bolt here and the water comes because the dead end, the water accumulated there, right? Fortunately, inspection of anchorage zones is simpler than free lengths of the stays. And how can you inspect? You can do hands-on inspection, which is really not non-destructive. I mean, you're opening things up, sort of like you're not destructing anything, but you're opening things up if you have that capability. You can do visual inspection using boroscope or other methods. You can do dissection of sheathing for visual inspection of fillers, strands. This is again not non-destructive. You can do again material sampling and testing for anchorage zones. The second priority to us is the free lengths of the strands. So once we see what's going on at the anchorage zone, there needs to be a method to look at what is inside, what's in the free lengths. One applicable method is magnetic flux leakage, which uses a magnet. There's a hoist, you just pull it up, it magnetizes, and you can measure the leak from the path of least resistance, and you can detect corrosion, but this method is not for detecting superficial surface corrosion, so you won't be able to determine the point surface corrosion starts. There should be a notable corrosion already taken place. 5 to 10, I would call it closer to 10%. So 10% of the strand needs to be gone by corrosion, right? Or 5% in the best case scenario. The other method is the global health assessment. This is not just looking at the stays, but the holistic cable stayed bridge. You can use vibrational methods to estimate stay forces and compare them with healthy conditions. So you can see, this is just a sample from literature. You can determine the forces and you compare it with the healthy conditions. You can look at the changes. For example, in this example, there are 3 cables with some notable changes, so that indicates something is wrong. Doesn't indicate there is a corrosion, but it indicates something is wrong that should trigger a more comprehensive evaluation. So our research approach was to focus on high-risk areas, which is the anchorage zone. Boroscope inspection, completely non-destructive. We didn't open anything. Environmental condition monitoring inside the states, again, non-destructive, non-invasive. And the third one is stay force estimation, which is the global health assessment. So what are the forces inside stays, and compare it with the original healthy conditions. That's the global assessment. So these are the 3 things which I'm going to be presenting. So if we detect any corrosion or any indication of deterioration, then the most difficult, the more expensive approach, which is magnetic flux leakage, might be an option, in which you, as I show you the photo, you slide a magnet, hoist it, and detect any significant corrosion, 5 to 10%. So I have some signing. So right now I'm talking about visual inspection, and then I will move on to environmental condition monitoring, and finally vibrational testing. So you're going to see what stage I'm at this presentation. So we were lucky because there were existing drain holes, and we looked into options how we can go into and do a visual inspection. Because if there's any water going into the system, this is a perfect location. There is a grease. Are there any water accumulation on top of the grease? How do those strands look like? Do you see water running down, or do you see them dusty? So these are the things that we wanted to see. We reached out to vendors, we did the research, and we found the dual camera option to be the most suited, because when you are probing it, you want to see the side as well as the front, because side is the sheathing, or side of the stay. So this was the best option, and we looked at which one could fit. 6 millimeter, which is around 1/4 inch. So that's the device that we used. You have a joystick, and you can adjust the angle, or the viewing location of the probe. We also use some aluminum wire because these are quite flexible, and we want to go upwards as well, so you need something rigid. You can see how we are doing it. This is Suresh Dungal. This is the drain hole. This is bundled with aluminum wire. We use electrical tape to stitch them at every foot or so, and we're just gliding it all the way up as well as down. Down is a dangerous location. There is grease. You don't want to put that probe into the grease, so you have to be careful. But up, it's free. You can go as much as the length permits, and we use the entire length to go and see what's inside. 14 stays were inspected, so it's a good sampling. 250 plus photos were taken. You can see the photos. Stay 1A, this is the north side of the pylon, the first stay. You can see how this is up, this is down. You can see the grease. You can see the side view. Grease subsided a little bit, but no water. We don't see any water. You can see this is another looking up. Stay 7A, 10A. So pretty much the same. Looks very nice, looks like brand new. Dust is a good indication. We like to see dust everywhere. It indicates that there wasn't any water running down. So pretty good condition. We didn't see any epoxy coating damage or chipping or any indication of corrosion by any means. Dusty, which is a good condition. We also collected some grease samples, because the question is, how is the grease doing? Is it like keeping the viscosity, consistency, what's the color, etc. So we inspected these samples, and they appeared to be in a good condition. We didn't notice any stiff or any unusual visual changes in these samples. The second one, so I'm done with the visual inspection. The second question we asked, yes, okay, good. We don't have any water. We don't seem to have any corrosion, but how is the inside doing compared to outside? Meaning that, is it a really humid condition? Is it suitable for corrosion? Because again, we are looking at the anchorage zone, but we didn't look at what's going on at some other locations. So we want to understand, is it more humid? Is the condition suitable for corrosion? Because you need moisture and oxygen. So if you have humidity, there's oxygen for sure. So you might have some corrosion. So that's the objective. So again, we looked at what's available. again, we want to use the drain holes. Those holes really came very handy in this study. The first, we think about using this miniature loggers, which is produced by Omega Engineering, it's a major company. And then we looked at this probe-based loggers. So probe-based for this project was a better option. That's what we used because the insertion dimension is smaller, 0.7 versus 0.5. These are the main body. You attach it at any location outside based on manufacturer's data. These are really rated for the harsh conditions, minus 40 to 160 Fahrenheit. As well as data downloading is easier because you can do it wirelessly, Bluetooth. So this was definitely a very clear winner for our study. So that's what we used. Battery life, I put a question mark because what the manufacturer is suggesting, we found it to be very different than the real battery life. So, you know, battery life is a big question mark, which I'm going to come to that later on, very soon. This is the placement plan. You can see Toledo is here. This is the north side, north of the pylon, named A stays, which is the Toledo side. B stays, Maumee side. And you can see these are the location of the loggers that we put. Very important because what's inside is not that important. What's important is the differential. You have to differentiate, take the difference between external, right? Of course, it's going to be humid. We are not expecting dry conditions on top of Maumee River, but is it much more humid than external? So very important to have these external loggers. We only need one, but we use two because something might happen. It's a site condition, open, loss of snow. So we used two external, as well as we used 6 internal. So these are going into the inside of the stays. More than what we needed because we expected failures. It's a harsh condition. Yes, the loggers based on manufacturer are rated, but we'll see. We got some failures, so we really oversized. We used more than what we need in terms of sensors. So you can see how they look. This is the internal one with the probe. You can see the ruler, it's about 4 inches length. There is an attachment point. You can attach anything, but we attached aluminum wire to make it stiff because you don't want this to bend and go into the grease. Humidity sensors, there should be no saturation. Humidity sensor, if you have rain, it is dead. You lost it. So the humidity sensor should always look up. If there's any water run down, it should go down. It shouldn't go up to the sensor. So that's an important consideration. We also use this automotive wire loom tubing because of the vibration. The drain hole has sharp corners. Of course, any hole will have some corners and it might cut the cable. So you want to really put it, and we saw that it even cut this one. We didn't have any failures, but at some locations we saw it started to eat this tubing. So it's definitely recommended. This is the strap that we used for attachment. You can see how we are doing it. This is the bundle, probe, cable, aluminum wire, tubing together, stitched with electrical tape. So the hole should be, you know, it was suitable. We measured everything. You can see this is how we attached the logger, a lot of zip ties. These are different stays. And as you can see, the cable goes down and the probe should go up. If it goes down, any water here would run down, which is something that we don't want in this study. And 2 external, one to the north side of the pylon, the other one is the south side. You want to put it in a radiation shield because you don't want direct sun exposure. And we check the consistency. I'm going to show you in a minute. Both measured exactly the same temperature, exactly the same humidity. This is the installed version, installed logger, which is very small. You cannot see it clearly, but if you are driving by, you can see these definitely. So two issues. The first one is battery life. We had to replace batteries. Battery replacement is not something very user-friendly. You need to open up the device. There is a dehumidifier bags in it. You have to replace it, replace the battery, put it back. So it's something that we had to do. This is the battery that's used. So based on the manufacturer's data, the battery life 5 years. This is what we did. Power saving mode enabled. We use logging interval of 30 minutes. So even with 1 minute interval, it should last 5 years, but in our study, it lasted 9 months. So that's why I told you, the manufacturer's data may not be representative. Some of you might think, oh, maybe the loggers sat on the shelf for long. We checked the battery manufacturing date, and it's written on the batteries, and it was 24 months old. So even if you count all the days that the logger were sitting in the shelf, doing nothing or not recording anything, 24 months is still not 5 years. The second issue is the logging interval. We don't need very frequent measurements. 30 minutes is more than enough for our purpose because things do not change. This is not like an instantaneous change we are looking. It's the long-term monitoring. So this is the configuration we set it up. So if you set it to 30 minutes, there's a memory inside the device, and it would let you record 1.8 years, right? Which is what you want. But something happened during April 9th data download. It switched back to the default 1 minute, which we didn't realize. So what happens if that happens? Your memory would be full in 21 days. So this is something we experienced. So the recommendation is that whenever you download, you have to check your logging interval all the time. You don't want it to go to 1 minute and then stop recording data. So we lost some data because we were expecting 1.8 years, but 21 days. So we lost a couple of months of data. So temperature, you can look at the temperature. So let me introduce you the colors. So the black one is the baseline. This is outside. This is external temperature, right? Color lines are stays, 2A, 8A, 15A. These are inside the stay. So if you look, as expected, it's an enclosure. Temperature is going to be higher as expected, and it is 23 degree higher for A stays. This is Toledo site, north of the file long. If you look at B, very similar. It's 19 degree higher. This is happening around March, so temperature is higher as expected. We had some sensor failures. We were expecting that to be 8B was found non-responsive during one of the site visits, so we took it, but we already had more than enough sensors, so we ended up with 2 external and 4 internal versus 6 internal. Relative humidity. So relative humidity is something really misleading. It shouldn't be really used for this purpose. So if you look at the relative humidity, you might conclude, oh, it's good. Inside is less humid, which doesn't make sense. Inside is not going to be less humid. It's an enclosed area. What is missing here is the temperature, because inside temperature and outside temperature different and substantially different. We are talking about 19-20 degree difference. Humidity, it's relative, right? So it's relative to temperature, so shouldn't be used. So what we should be using is a measure which is called dew point, which is a combination of temperature and humidity. So it takes account of both of those. So if you look at humidity, 50% humidity, 50% humidity, 50% humidity, right? But there is much more moisture or water in this case. So relative humidity is saying that 50% of the cup is full, but the cup size is dependent on the temperature. So as temperature gets higher, air can hold more moisture, so the cup size gets increased. So if you look at dew point, which is the absolute measure, that's what should be looked at, dew point 37 degree, it indicates much less moisture than 74. So that really what should be used. Maybe you are using it already when you are checking temperatures during summertime. This is for humans, but still it's a good indication. So if you're checking dew point, if it is 55 to 60 degree, you would feel it comfortable. But if it gets higher, so 74 is really oppressive. You are going to feel that it's really dense. The air is filled with humidity, right? So if you look at dew point data, of course, we have larger dew points. As you can see, the black one is external, color one's internal sensors, and you can see substantial increases inside in terms of dew point or in terms of humidity. But the good news is that they are typically at the lower points. We don't have a peak point and then going up, with a few exceptions, maybe one exception, which is this one, which is a minor 5-degree exceedance, which is acceptable. So again, like we are not looking at a couple of degree difference. Of course, it's going to be different. Inside is going to be, it's an enclosed area. It's expected to have more moisture in it, but we are looking at a trend that inside is consistently humid. There's like a very substantial difference. You know, if you look at the data, we don't see that. It's very, very similar. In many cases, lower. There are some exceedance, but it's not exceeding at the peak points, with one exception. So we didn't have any concern for excessive humidity. B is really similar. If you look, all the exceedance happening at the low points, and we know the time, we know the date. It's either day is changing, it's 5 a.m. in the morning, or at the end of the day, 7 p.m. So things are changing. Inside is catching up later. What happens outside is seen by the inside later on. So there's, because of that delay, we have these exceedances, but we are happy. We don't have any concern in terms of inside conditions. It's very similar to outside. This is sensor consistency. How are we measuring? You know, do we have some reliable sensors? Yes, we do. These are the two external sensors. They are measuring the same thing, external temperature, and you can see hard to distinguish. They are on top of each other, so it is pretty reliable. In terms of temperature variation, this is dew point variation, so we are measuring the same thing, consistent. So as expected, inside is slightly more humid. However, there is no evidence of sustained or any notable excessive moisture inside. It stays 7.5 months. That's the entire duration. But again, the conditions same. We didn't have any indication of any month or any time that we have excessive inside moisture accumulation. So we felt 7.5 months is suitable to reach our conclusions. This is the final part, maybe the most interesting part. We did it for the first time. This is the global health assessment. What happened? Cable tensions are very important. What happened to cable tensions since initial construction, 2007? So the big question is, do you have the initial values, which is the healthy baseline conditions? Because once you measure it, you are going to compare it with the original healthy condition, which you need to have it. So you can have it using experimental methods. Somebody might have measured it, or even better, you might have your contractor measure it using load cells. So load cell measurement is the most accurate, most reliable method, because it's not non-destructive. So they really use the anchorage points, install the load cells, and they really mechanically measure it. It's not a sensor measuring it. So we are fortunate, we have the contractor load cell measurements. So we have the healthy baseline values for that. So we have two options for our measurements. The first option, some of you might be familiar, would be accelerometer. So this is the really industry standard, inexpensive, commonly available. Theoretical basis, we know it very well. You use accelerometers, which is pretty small, 2 inches. There's a data acquisition system. You run it with a cable, so it's a wired system. So you can see, for example, there is one accelerometer attached here. The wire, comes down, which is here. Sorry, it is attached here. I think this is grounding something else. It's not what we are looking for. So you glue it to the surface, run the cable. Yes, a bit labor intensive, a bit tedious. You have to do it one after another, and it might take maybe 2 days, but that's something done commonly. The problem with this one is you are measuring the outside vibration. So this measures vibration and then you convert it to force. This is good for grouted stays, right? Because the grouted state, everything inside and outside would vibrate at the same frequency. That's what you are going to be measuring. But VGCS, as I mentioned, inside is not grouted. So inside might be vibrating and sheathing might be catching up a little bit later. So they may not be vibrating as a unity, especially at the lower as well as higher points. So for VGCS, think about this. For the entire state to vibrate with the same frequency, you need to get the measurement from the central location, maybe central 1/3, right? So this really makes accelerometer measurements impractical, because how are you going to be installing those accelerometers and then running cables? Yes, it's doable, but it would be very expensive and perhaps unnecessarily complicated procedure. The second one, we looked at how can we use some mechanical engineering approaches. They use vibrometers, especially for automotive sector. Using vibrometer, you can measure the vibration of a car engine or anything vibrating from a distance. It's definitely, you don't need any cables, you don't need to install anything, you're just shooting the vibrating object. What you need is the vibrometer, scope for aiming, lens, different lengths is available, tripod. It should be precision because you're really shooting at a distance, data acquisition laptop, as well as power supply on site. So this is what we used, and that was the first time we used it. We really enjoyed using that. So what you are measuring is the first natural vibration frequency, right, in hertz. So that's the only thing you are measuring. Everything else in this equation is known. L is the cable length. T is what we need. T is the cable tension, and M is mass per unit length, which we know. We know how many strands in it. We know the mass of the sheathing, so we know all of these. Of course, this is a simple equation. It comes with some negligence, not considered, not neglected. It's neglected. Sag extensibility as well as bending stiffness. There is some bending stiffness. These are not, this is not a string, right? So we are neglecting, so there is some error involved. First of all, there was an accident in Craig Bridge and the bridge was closed. And we used that occasion just to test the setup. We didn't intend to measure anything, but we wanted to just see how the setup works. Are we able to aim? So this was sort of like a test run for us. So, we went to Craig Bridge during night. During daytime, we couldn't see the laser. It's such a small, it was a sunny summer day. So this is not something you want to do on a sunny summer day. Maybe a dark winter day might be suitable, but we went with the night measurement for visibility purposes. Signal strength is low. We have a huge distance in this case, but we just tested the setup. You can see how we are shooting the stays. This is the actual measurement from the deck. ODOT was really kind to close one of the lanes, because when you are measuring, you don't want trucks passing by and creating vibrations. There's always a concern, even with one lane closed. So you set up, we didn't have binoculars, so we attached homemade binocular versus a scope, but it worked for us. Even with a naked eye, you can see it. Nighttime is a perfect time. Sometimes if there's a street light coming between you and the target, then yes, you don't see it, but you have to change your location. So this street light created a problem for us, so we had to change a couple of times. You can see, even from the photo, you can see how we are targeting. One thing you might ask, your machine is vibrating because the deck is vibrate, so the measurement device should be on a surface which doesn't vibrate, because if your machine is vibrating, how are you measuring something which also vibrates? So there's a scientific basis for it. We don't want resonance condition, right? So we don't want deck vibration frequency to be similar to the vibration frequency of the target, which is stay in this case. So that's, if that happens, this method is not for you. It's not gonna work. You are not going to get any reliable measurements. So luckily we measured from Craig Bridge. The bridge was closed. We didn't have any vibration. So we know, we target the deck of VGCS. So we know the VGCS deck vibration from that location. So long story short, VGCS deck vibration, we found it to be 7.6 hertz, but the stay vibrations overall from 0.6 to 3 hertz. So we don't have any close overlaps. So we didn't have this problem. So, but it's important, you have to check whether are you getting close. And I can see that in some cases, depending on the stay length, you might hit the same frequency, then this method will not work for you. You can shoot it from the land, not on top of the bridge, but from some other location if you have such a location. So these are the tensions, 50% sampling, we measured 2, 4, 6, so every other. Of course, it's temperature dependent because these are long cables, steel cables. This is, you would remember this equation from your university years. Temperature change, modulus of elasticity. So luckily, contractor measured the takeoff or healthy condition temperatures. Some of them, I mean, temperatures are a bit, is it in the sun? Is it in the shade? So you gotta take some average. So it's not like an exact science. You don't have, because every part is seeing sun differently. This is what they used. So we did the temperature adjustments, right? So quite substantial, up to 10% adjustment, on average 6% adjustment. This is stay tensions. You can see deviations. A positive deviations indicates that we estimated larger than the healthy conditions. So I'm going to come to this one. So these two needs to be ignored. Our largest discrepancy is 10%, but other than that, if you look at these very nice numbers, some of them bang on 1%, 2%, 3%. We have 8, 10, and 6, so which is acceptable considering all the errors that you might be accumulating. If you look at B is even better. You can see 0% bang on, up to 9% deviation. That's what we got. 2 and 4 exception, because 2 and 4 are, let me go back, these are pretty stiff. If I can find that photo. Yeah, 2 and 4, 2 is this one, 4 is that one. So these are very stiff, short stays. Outside sheathing vibrates different than inside, right? So you need some long lengths to have that unity vibration. So for this short, I'm assuming 1, 2, 3, 4. The first 4 inside and outside would be vibrating differently, and any measurement, including accelerometers, will not be accurate for those short stays. So those are excluded. Very good correlations. You can see this is lift off, that's what contractor measured, and blue one is what we are measuring, force plus delta F. Delta F is temperature adjustment. We measured it on a summertime, contractor measured on a winter day. So you can see up to 10%. These are including everything from Craig Bridge. Distance was high, signal strength was low. We didn't intend to measure anything, but pretty good. 3% deviation, 1%, 4%. So that really bring up the idea. The measurement can be done from Craig Bridge. You don't need to really close any lane. It's ideal for future measurements. Again, if you look at B stays, beautiful, very nice deviation. Some of them bang on. So it's really remarkable using a laser signal, using some approximate equations, neglecting something still, you can get pretty good accuracy. Looking at this 2-3% up to 9%. Pretty good. What we are neglecting is stiffness of the stays. Temperatures are approximately, you can see that it can affect up to 10% sunshade. So definitely a couple of percentage deviation might be happening here. Measurement method can introduce 1% in frequency. That would translate 2% in the estimated force. So definitely there's some errors made, but under 10% is very acceptable within the margins of accepted deviation. So pretty good results. We recommend this measurement can be done at every 4 years to measure how things are going as a global health assessment. In the next measurement cycle, some attention can be paid to stay 10, 11, 12. These are like 9, 10%. So these are the higher deviations. So some more attention could be paid. Measuring from Craig Bridge would be very good. You don't have to close the lane, very comfortable location. There is not much vibration going on. So that is pretty much it. Slide number 58. My target was to finish it in 45 minutes. I have 4 more minutes to conclude it before we take your questions. So overall findings, again, most critical condition is still strands inside the stays. Literature, case studies, subject matter expert interviews, we interviewed quite a few experts, indicate that you have to start from anchorage. Anchorage is the location that corrosion starts. You can do visual inspection or material sampling testing. So there are methods which I presented in this presentation. We should be able to get it as a handout. Global assessment includes cable force assessment method using laser vibrometer. Free length is more difficult. You should only consider it when it is necessary, when you see any corrosion at the anchorage zones. You can use magnetic flux leakage or pulling and replacing a few selected strands. This is what the manufacturer, Dividac, considered it. This is a unique signature bridge, and they designed it such that you can pull a single strand. I mean, probably not as easy as it sounds, but in theory, you can pull a single strand, take it to the lab, cut it, do whatever. Of course, when you pull it, you are replacing it with a new one. So it's going to be a replacement operation. You just replace 1, 2 from each side. You are done, take the samples to the lab, inspect. So at the end of the day, it might come up to be cheaper and more practical than MFL testing. Boroscope, visual inspection, very good condition, no signs of damage, chipping or corrosion. It's dusty. We didn't notice any excessive moisture inside, outside is pretty similar. Stay force less than 10%, which is again not anything that's concerning to us. Recommendation, there should be a continuation of monitoring. So it's not just what we did, but ODOT has a comprehensive long-term monitoring program for all bridges. So that should really continue. On top of that, 4-year measurement cycle, cable tensions could be estimated. If any evidence of strand deterioration is detected, free lengths could be considered using either a custom magnet, which is magnetic flux leakage testing or pulling and replacing a few selected strands. This is a study, somebody needs to sit down and look at advantages, disadvantages, cost, etc. But we are nowhere close to this. So we didn't notice anything with the anchored zones. So our recommendations is, this is in the future if needed. It may not even be needed anytime soon. So it's almost 2:44, 2:45. I thank you very much for your attention. So we have a good 15 minutes for any questions.
All right, thank you. We do have our first question submitted by Rexford, and he says, how long do you predict that this bridge will last?
So that is really, that's a good question, but I really don't have any prediction. But what I can tell you, it's a high cost, high quality bridge, stainless steel sheathing used in the stays, epoxy coating, we didn't see any deterioration. So I cannot give a number, but my estimation looking at the cables, it's going to be on the higher end of the life of a bridge. So it's a good one, in my opinion.
All right, thank you. As we wait for additional questions, I want to mention that Jennifer is available on behalf of ODOT's research section. So Jen, did you have any comments to share on behalf of the research team?
Not necessarily at this point in time. We do want to thank the research team for this research project, and we appreciate the follow-up for the results presentation. It's really good information, and we're very happy to share it with anybody that may be in need of this information.
All right. Well, thanks, Jennifer. As a reminder to our audience, the questions box is open. Sirhan, any other comments you'd like to share while we're waiting for additional questions?
I mean, the methods, this is a specific application, but the laser measurement method, environmental condition monitoring, as well as, the other parts. So you can really apply it to any bridge. It's possible. Laser measurement in particular, it's you don't have to close any lane from a distance. You can measure it. So it is a very applicable method overall. So I recommend people to consider it for their own bridges.
All right, thank you. Well, at this point, we do not see any additional questions being submitted. So we will go ahead and conclude this research results presentation. Oh, here we go. We have a question from Bradley. He says, was there a fire on the bridge a few years ago? If so, was there any damage to the bridge cables?
That wasn't something, that's a really good question, but it wasn't something that we were looking for. We didn't look at any specifics, so I am not able to answer that question. But as far as the locations that we inspected, anchored zones, we didn't see any indication of any fire, but I'm not really sure about the specifics or what part got involved in that fire. So again, I should emphasize investigating a complete bridge is a big undertaking. So what we did here is a limited investigation of the stay cables. We looked at the anchored zones, but there's a lot other locations of the bridge that should be and that are evaluated based on a regular inspection program, which is not part of our study.
All right. Well, we do not see any additional questions. So, here we go. Question from Amjad. Are there live sensors permanently installed on this bridge?
Yes. Still, we have loggers installed. They are recording data with 30-minute interval. So once you install it, it's really easy. You can go every 2-3 months, download the data using Bluetooth. you have to be careful with the battery life because it's not lasting too much. So, but yes, the question is, we have sensors on the bridge still.
All right. I think that is the last question. So we want to thank the research team for this presentation today. We really appreciate it. And thanks everyone for your participation, and enjoy the rest of your day.
Thank you very much for giving me this opportunity. I really enjoyed conducting this study. Thank you.
Thank you.